We're going to get started with our 5 steps of hypothesis testing, and we will begin this time with step number 1, which is to choose the appropriate statistic. In the Bear Handout, you'll see some examples of how we could think through the choice of our statistical test. And we could use the diagrams that I provided for you to make those decisions. You're going to choose your test based on a number of factors, all of which will come from your exploratory data analysis. This means you look at your data and you make some determinations based upon the levels of the data and whether the assumptions have been met as to what test you can use. So generally you have to figure out your independent variable and your dependent variable. You have to look at the levels of the independent variable. Is it categorical or continuous? You have to look at the levels for the dependent variable. So hopefully that is a continuous variable, something we're measuring for the dependent variable. And if we have categorical independent variables, then our choice is going to be pretty simple. It's actually the example that we're going to use following along here. Another important thing to consider are whether the assumptions for the test have been met. All of our tests are built on certain assumptions. If the data do not meet the assumptions, well then the conclusions we draw from the data may give us erroneous results. Results that aren't replicable, results that don't hold up. So we want to make sure that those assumptions have been met before we make our choice. Now this choosing of the appropriate statistic may actually be the simplest of the 5 steps, especially as we're learning, because the answer in almost every case of which test should you use is going to be the one that we're learning about right now. If I'm teaching you about a z-test, we're going to use a z-test. If I teach you about a t-test or an ANOVA or correlation, that's the test that we're going to use. But along the way, I'm going to show you how you can make that decision so that you will know with new data as you go on to other classes which test you should choose. We're going to learn 3 tests next week. The first is the z-test, which we use when we're comparing a sample to a population mean and we know the standard deviation of the population. The second test we'll learn is very similar, but it's called a t-test. And this is where we're comparing a sample mean and a population mean, but we do not know the standard deviation of the population. What we'll do is we'll estimate the standard deviation of the population using the standard deviation from our sample, but that also means that we're going to have to adjust for degrees of freedom, something we learned about last week. And then the third test we'll learn about is a proportions test, where we're comparing the proportion present in a sample to the proportion present in the population. Using our baby weight example, we have a world population of 7.5 pounds. We don't know the standard deviation of this population. It wasn't present in the literature review that we did. And we have a sample mean of 11 pounds. And we need to decide, does that mean of 11 represent a world mean of 7.5 or the mean of some other and as yet unknown population? A population defined by some kind of an effect where babies are just born larger. Now let's go on to step 2. Choosing a null and alternative hypothesis. To explain why we test a null hypothesis, let me start with something very simple. The idea is called the method of contradiction, and you'll see this playing out as we try to answer some really simple questions. Let's say we start with a hypothesis that there is life on other planets. Well, the question very simply is, could you prove that true? Well, sure. What we do is we go to another planet and we discover life on that other planet. We have definitively demonstrated that it is true that there is life on other planets. But could we prove this hypothesis false? We go to a planet, no life on that planet. Go to another planet, no life on that planet. Go to 100 other planets, never find life on other planets. Does that mean that there's not life on other planets? Certainly someone could say, well, maybe the life was hiding from us, or maybe it's a different kind of life, or maybe we just haven't gone to the right planets yet. So we've not disproved that there is life on other planets. All we know is that we haven't found any proof of it. We cannot demonstrate that this claim is false. But let's take a different hypothesis. one that says that there is not life on other planets. Now, is that something that we could prove true? Well, certainly if we went to other planets and we did not find life on any of those other planets, we could say that the evidence supports the claim that there is not life on other planets. And could this hypothesis be proven false? Absolutely. We go to another planet, we find life on that other planet, we have definitively disproved the claim that there is not life on other planets. This works because the statement that there is not life on other planets is falsifiable. You see, with our first two hypotheses, or with our first hypothesis that there is life on other planets, it's not falsifiable, and it means it's just not going to work for our purposes of testing. However, the statement that there is not life on other planets can be supported by evidence, and it can definitively be proven false. This is a claim which is falsifiable. Now, falsifiable doesn't mean that it is false. It means that it makes sufficiently precise predictions that if it was false, we could demonstrate it. So with hypothesis testing, we don't begin with a statement that we want to prove to be true. Instead, we begin with a contradictory statement, that method of contradiction, one that we can demonstrate to be false. And in showing that it is false, we can demonstrate that the alternative must in fact be the better explanation. So we do not begin with a hypothesis like Siberian babies weigh more than the world average. We start with a falsifiable hypothesis like Siberian baby weight is the same as the world average. It's not at all different. And this is called a null hypothesis. The null hypothesis states that there is no difference between the sample mean and the population mean. Other examples of a null hypothesis might be examples like these. There will be no difference between the scores of the deaf rats and the hearing rats. The scores this year will be the same as the scores from last year. Notice how saying that something is the same is equivalent to saying that there is no difference. The men's scores will be no different than the women's scores. No matter how you write it, we're saying that there's no difference between sample mean and population mean. They are the same. And so with our baby example, we might say, in words, the average weight of babies born in Siberia will be no different than the world average of 7.5 pounds. And in numbers, we would write h sub 0 colon mu equals 7.5. We're saying that this sample is drawn from a population with a mean of 7.5. Another way that you may see a null hypothesis written is mu1 equals mu2. We're saying that there are two groups, and each of these groups is drawn from a population whose means are equal. But then we would pose an alternative hypothesis. The alternative hypothesis is our other explanation, the one that if we reject the null, we will conclude that our alternative is in fact the case, that it is true, that it does best represent the facts as they are available. The deaf rats will have a better sense of smell than the hearing rats. The drunk people will make fewer driving mistakes than the cell phone users. Golfers are more likely to be struck by lightning than are swimmers. Or, using our baby example, we would say, as our alternative hypothesis, that the average weight of babies born in Siberia will be different than the average in the world of 7.5 pounds. And expressed in numbers, h sub 1, or h sub a, colon, mu does not equal 7.5. So again, our null hypothesis will always be written as h sub 0. Our alternative hypothesis will be written either as h sub 1 or h sub a. I prefer the h sub 1 because sometimes we have multiple alternative hypotheses, so we can use h sub 1, h sub 2, h sub 3 to distinguish them from each other. Now this leads us to another subset of these alternative hypotheses in which we may establish a direction of change in the alternative. This is called a one-tail or two-tailed test. The tails referring to the tails of the distribution of the sample means. In a directional alternative hypothesis, we would speculate that the sample mean will be higher than or will be lower than the population mean. We're establishing a direction of change. We would write this directional hypothesis as h sub 1, mu is greater than 7.5. And this would be for a greater than or higher than hypothesis. If it was directional to the lower tail, we would say h sub 1 mu is less than 7.5. This is a one-tailed test where we have divided our distribution of sample means such that 95% of the scores are under the curve and 5% are either in the one-tailed test left or alternatively one-tailed test right. A way to recall this and remember is that with a one-tailed test, we can only go one direction, either higher or lower. Now the alternative is a two-tailed test, a two-tailed alternative hypothesis, in which we are not saying which direction the change will occur, only that our sample will be different than our population. A non-directional hypothesis might say that the sample mean will be different than the population mean. We would write this as h sub 1 mu does not equal 7.5. We're not saying whether it will be higher or lower, just that it will be different, not equal to 7.5. This is called a two-tailed test. With our distribution of sample means, you can see that we have included 95% of the scores underneath the curve, and we have split that 5% into the two tails, leaving us 2.5%, or a proportion of 0.025, in both the upper and the lower tails. With a two-tailed test, the changes can go in either direction. So now we can apply this using our baby weight example. Our null hypothesis, h sub 0, mu equals 7.5. The average weight of babies born in Siberia will be no different than the world average of 7.5 pounds. Our alternative hypothesis, h sub 1, colon, mu does not equal 7.5. The average weight of babies born in Siberia will be different than the world average of 7.5 pounds. Now we're moving on to step 3, selecting a level of significance, or some criteria that we will use to determine whether our sample mean is truly different than our population mean. And I want to show you 3 ways that we might go about making this determination. The first is this, that the test statistic exceeds a critical value. The critical value is a fence. It's what we use to determine if our test statistic is significant, or to be more specific, statistically significantly different. Now, we've explored this setting of a critical value as we've experimented with z-scores before. We know that there's a very specific z-score, 1.96, positive and negative z-score, that divides our curve into 95% underneath the curve and puts that 5% out into those two tails. That 1.96 can serve as a critical value or a cutoff score. Scores, test statistics greater than 1.96 or that exceed 1.96, those are statistically significantly different than the population mean. Let's use an example that you may have encountered if you've grown up here in the Ozarks. Maybe somebody says, hey, do you want to go cow tipping? And this is a very bad idea. It would involve sneaking into some farmer's field where there's cows, and you might tell your city friend, all right, we're going to sneak up to these cows and we're going to try to push them over while they're sleeping. Which is a bad idea for a lot of reasons, one of which may be that not only are there cows in this field, maybe there's a bull in this field. And the cows, they don't like to be disturbed while they're sleeping any more than you would, and they might get mad, they might chase you. So here's the situation. you sneaked up on a sleeping cow and too late discovered that it was a bull. And now this bull is chasing you across the field. Your goal is to get over the fence to safety. Does it matter whether you are in the middle of the field or even right up next to the fence in terms of your safety? The only place where you're truly safe is over the fence. And this is how critical values work. We set these two fences. They are established by either 1.96 or, in a case of a one-tailed test, a 1.65 or 645. And then we look at the test score to see, is that score outside the fence? Has it made it over this critical value cutoff score that we've established? To the left, we could have scores outside of the fence. If the test value is greater than our right fence critical value, we say that's outside the fence. And in both of these cases, a statistically significant difference between our sample mean and our population mean. But anything inside of those two fences is non-significant, whether it's right next to the mean in the middle of the curve, or even it's approaching that 0.05. If it's a 0.06, it's still inside the fence. It is not statistically significant. So the way that critical values work is you have one very definitive cutoff score, and only scores that are less than or equal to that cutoff score are statistically significant. But there's one other caution that I want to give you, and that's specifically about one-tailed tests. For a one-tailed test to be significant, the change has to be in the direction that we have hypothesized. So in this example, we've hypothesized that the sample mean will be greater than the population mean. And so we have put 95% of our scores under the curve and 5% out there in the right tail, represented by that purple shaded area. I've also included two dotted lines which indicate where the two-tailed test levels of significance would be if we were using a two-tailed test. So we run our test and we discover that our sample mean is way out here to the left. It's in an area that if we were using a two-tailed test, it would be statistically significant. And yet, using a one-tailed test, because the change has gone in the opposite direction as what we predicted, this would not be statistically significant. This finding would in fact be non-significant. So how does that make sense? Let's say we're using some kind of drug that we want to increase your ability to concentrate as you're studying. If that drug doesn't have an effect, or if it makes your ability to concentrate worse, neither of those are useful outcomes. Only if the drug increases your level of concentration, statistically significantly, is it a worthwhile outcome. When we use a one-tailed test, the direction of change for our sample has to be in the direction that we hypothesized for that difference to be statistically significant. The second way that we might use to determine whether changes are statistically significant is to look at the p-value. Is the p-value less than 0.05? Our p-value is the probability of finding a given test statistic if the null hypothesis is correct. And what we do is establish an alpha level. Alpha being that funny fish-shaped symbol, which is the Greek letter A. That if our p-value is less than our alpha value, then our test is statistically significant. We would reject the null hypothesis. Now I said that the p-value is less than 0.05. However, 0.05 is not the only level of significance that we could choose. The important thing is that we should choose our level of significance before we begin our process. We can't run the study, find the p-value, and then set an alpha value that makes our p-value statistically significant. In fact, we have to place our bets before the horses run, if you will, and then after we have collected our data and determined our p-value, see whether the p-value is less than 0.05. But we could also use other p-values. 0.05 is the most common, but In medical research, where the stakes are higher, it's not at all uncommon to find p-values of 0.01. Or in polling research, where the stakes are lower, where the cost of an error is not nearly so high, we might find p-values of 0.1. 10% of the scores, rather than 5% of the scores being split out into those tails. So for most tests, it is safe to assume that we're using an alpha value of 0.05 and a two-tailed test. So here's a hint at how you can interpret these alpha levels. Think of $1, which is 100 cents. And then you can think of 0.05 as a nickel, or 5 cents. When you come across significance values in your test, you just interpret those as you would counting change. If the significance value is 0.32, that would be like 32 cents. We're looking for values less than 5 cents. Is 32 less than 5 cents? It isn't. This is non-significant. If the significance is 0.022, that would be like 2 cents. Is that less than a nickel? Yes, it is. Our p-value is less than 0.05, and it is statistically significant. There may be times when you encounter a significance value of 0.000. Does that mean the probability is 0? It does not. What it means is the probability is so small that we can't capture it with just those 3 decimals. It might be 0.00002. When you have a significance value of 0.000, you should write that up as p less than 0.001. Going back to the early days of using p-values, the original idea was not that we had one very strict and stringent cutoff value and that only values definitively less than 0.05 could be counted as statistically significant. Rather, Dr. Fisher suggested that what we should use is these p-values to determine the level of support for our hypothesis, such that p-values less than 0.01 indicate very strong evidence to support the alternative hypothesis. P-values from 0.01 to 0.05 indicate strong evidence to support the alternative hypothesis. Values from 0.05 to 0.1 indicate weak evidence to support the alternative, but they suggest that it may be correct and we'll probably want to do further research. Values of 0.10 or greater indicate insufficient evidence to support the alternative hypothesis. Now, the third way that we might interpret whether values are statistically significant is to look at the confidence intervals. If the confidence interval around the mean difference includes 0, then our test is not significant. The confidence interval are the values between which the mean difference will fall 95% of the time. Now, we've experimented with confidence intervals before, but those were confidence intervals around a mean. This is a mean difference. This is subtracting the population mean from the sample mean. So a mean difference, or M sub D, you subtract one mean from the other. The null hypothesis, we've already said, tells us that we're testing a hypothesis that the mean difference is 0, that the scores are the same. The population mean and the sample mean are the same. There's no difference. The difference is 0. If the confidence interval around the mean difference includes 0, non-significant test. But there's another way of interpreting confidence intervals. We can look at the confidence interval around the sample mean and see whether that confidence interval includes the population value. So this gives us 2 ways of using confidence intervals. Well, let's say we've interpreted or we have calculated a confidence interval around our sample mean that ranges between 1.58 and 3.39. 95% of the time we're going to get a mean in between those 2 scores. If the population mean is 2.20, can you see how that is between our confidence interval values? Because the confidence interval captures the population mean, non-significant. But if we have a population value of 1 or a population value of 3.75, both of those population values are outside of our confidence interval for around our sample mean, and in that case, the test would be statistically significant. Now, it's important to know that these ways of interpreting statistical significance will give us the same answers. They will always agree. Now, in this example, I have an independent samples t-test. Let's look at the 3 ways that we could interpret. Number 1, our critical value with 14 degrees of freedom is a positive negative 2.145. Only values that exceed 2.145 are significant, and our t-value is 1.58. That does not exceed 2.145. Our p-value is a 0.135. Convert that to dollars and cents. 13 cents, is that less than a nickel? It is not. Our confidence interval around the difference, the lower bound is negative, the upper bound is positive. Well, that means that our confidence interval must cross 0. All 3 of these tell us exactly the same thing, that this test is non-significant. In this second example, we have a paired samples t-test. Let's look at the findings for this test. The critical value is 2.365, and our t-value is 2.75. 2.7 exceeds 2.3. Our probability is 0.028, or 2 cents, which is less than a nickel. It's less than 0.05. Our confidence interval, the lower bound is positive, the upper bound is positive, which means that 0 is not contained within that interval. All 3 of these findings tell us exactly the same thing, that this test is statistically significant. And so now let's apply this using our baby weight example. We would set up our step 3 with an alpha level of 0.05 using a 2-tailed test. Our critical value, positive negative 1.96. And so now we're ready to move on to steps 4 and 5 in our 5 steps of hypothesis testing.